Okay, good morning, good afternoon, and welcome to Biomass Canada Cluster webinar series. My name is Mahmoud Ebadian. I'm a research associate at the University of British Columbia working on biomass, bioenergy, and biofuel supply chain. I work with two research groups at UBC, Biomass and Bioenergy Research Group, BBRG, as well as Forest Product Biotechnology and Bioenergy Research Group. And today we will have the 7th webinar from the webinar series. If you have attended the previous webinars, we covered different topics on Canadian bioeconomy with focus on agriculture biomass. We had some discussion on producing dedicated biomass crops such as switchgrass, miscanthus. Also, we had a few presentations on pelletizing agricultural biomass and improving the quality of biomass using different pre-processing. And also we had discussion on application of agricultural biomass for bioenergy, biofuels, as well as biochemicals. And today we will have another presentation. Again, the focus is going to be on pelletizing ag biomass and also improving the quality using the different pre-processing techniques. Before that, let me again review the Biomass Canada cluster. This is a cluster led by the BiofuelNet Canada network and with the financial support from Agriculture and Agri-Food Canada Agri-Science Program. And also we have industrial contribution to this program. As you see, the overall objective, I guess, it's mainly focusing on Canadian agriculture and increasing the contribution of this source of biomass in Canada in the growing Canadian bioeconomy. In total, we have 10 activities or projects, and these projects, their focus is on different part of the value chain, including producing biomass, pre-processing, and also distributing feedstock from agricultural biomass resources for different application. Again, as I mentioned before, for bioenergy, biofuels, and also other bio-based products. A few housekeeping items as usual. So this webinar is being recorded, and after the presentation, you can have access to the recording and a copy of the slides on Biomass Canada website. You see the link here. As you see, we have two boxes in this platform, Q&A. Please type your question in the Q&A box, and then after the presentation, we address this question. And also, I encourage everyone to introduce yourself in the chat box. Again, as I mentioned before, this is a way to sort of socializing in this platform. Okay, with that, it's my great pleasure to introduce today's speaker, Dr. Ajay Dalai. He gave a presentation actually in December. He's leading two activities, two projects in this cluster. And the main focus, again, is on pre-processing agricultural biomass in order to improve the quality of local, like underutilized agricultural biomass in Canada. Dr. Dalai, he is a distinguished professor and Canadian researcher at the Chemical and Biological Engineering at the University of Saskatchewan. He has served as the head of the chemical engineering for from 2007 to 2009, and associate dean research and partnership in the engineering at the University of Saskatchewan for 5 years. In 2001, he was awarded a Tier 2 Canada Researcher in Bioenergy and Tier 1 in 2009. In 2012, he accepted the position of Special Advisor to VP Research Signature Areas of Energy and Mineral Resources. His research focus is bioenergy and value-added products from biomass, pollution control, and novel catalyst development from gas to liquid technologies, biodiesel production, hydrogen and syngas production, and hydroprocessing gas oil. Okay, with that, Ajay, we are looking forward to your presentation, and please take it away.
Well, thank you very much, Mahmoud, for a kind introduction, and good morning to you all. Thank you for joining for this webinar series, part of the Biofuel Canada Net. And I hope it will be an interactive session, and hopefully there will be a lot of good questions, and I will go from there. So let me share my screen. So, Can everybody see my screen?
Yes, yes, Ajay.
Okay. So you can see the title page.
Yep.
Okay. All right. So am I audible to all?
Yes, I think so, Ajay. You're good to
Okay.
go. Thank you.
Thank you. So today I'll be talking about the applications of thermochemical and hydrothermal pre-treatments in production of fuel pellets using agricultural residue. So the goal of this project, there are basically 5 milestones. So let me go through those milestones, and we are in milestone 3 right now. So milestone 1 is the production of torrefied biomass and hydrochar from agricultural residue. The second milestone is the production of fuel pellet from treated agricultural precursors. Third one is the optimization of biomass pellet gasification process for value for fuel grade syngas production. And then the fourth milestone is the scale up and piloting the new pelletization gasification process. And the important one is the life cycle and techno-economic analysis based on the work that we have would be doing on from all 4 milestones related to biomass pretreatment, pellet production, and gasification process. So let me give you a very brief background on why this project is important. If you look at this particular slide, you can see that in the world, we are still using 81% of the fossil fuel. The renewable content of the energy sector is 13%, and that's going rapidly. And we have some issues with the nuclear, but nonetheless, we have about 6% nuclear energy around the world. And because of this fossil fuel usage, as you say, the 81%, there is a lot of CO2 emission from this, leading to global warming. And that global warming, again, you see in this in the graph here. So over last 50, 60 years, due to industrialization, population growth, and demand on high quality of life, there is a lot more energy usage, especially from fossil fuel, that leads to the CO2 emission. And you can see that is every year there is a fluctuation of CO2, and so as the temperature. That's because in the northern hemisphere, we have a lot more forest than the southern hemisphere. And because of the photosynthesis going on in the summer months, more in the northern hemisphere where we have more forest, there is a lot more CO2 sequestration. Therefore, the CO2 concentration goes down to some extent. Therefore, the temperature drops. But as soon as we hit the winter in the northern hemisphere, where the photosynthesis is relatively inefficient, there is a lot more CO2 concentration increase over the globe. Therefore, the temperature rise. But nonetheless, there is a drastic increase in the upward trend of temperature anomaly over last say 60 or so years. There is a more or less increase of 0.6, 0.7 degrees C over the planet. And this cartoon again shows what is the impact of the global warming. It causes acid rain, soil erosion, deforestation, poor air quality, and most importantly, hazardous to biological system, including animal and human health. And if you look at the greenhouse gas emission in Canada, so these are given in sector wise, and we see that the transportation sector emits about 25%, oil and gas about 26%, and electricity generation about 9%, heavy industry about 11%, agriculture industry about 10%, and building industry about 13%. So you can see there is a greenhouse gas emission because of the energy usage from different sector. And moreover, there is of course, a large amount of energy or the CO2 emitted from these sectors. And when you look at the Canada's emission by greenhouse gases, about 80% from CO2, and about 13% due to methane. And we know that methane also has 21 times more greenhouse gas effects than CO2. And this methane emission from rotten biomass, etc., is also has to be paid attention. And I'm glad to report that Canada agreed to both Kyoto Protocol and the Paris Accord, but no countries around the planet was able to meet the Kyoto Protocol. And according to Paris Accord, Canada has pledged to reduce its greenhouse gas emission by 30% below 2005 levels by 2030. Developed countries, including Canada, are committed to spending at least $100 billion a year between 2000 and 2025 to help emerging economies deal with the effects of climate change. And now that's why the biomass becomes very, very important. It's a renewable energy source, and the strategy is to use the biomass for energy and other biochemical applications to reduce the greenhouse gas emission, and of course has direct impact on the global warming. And also there are abundant amounts of waste or the bioresidue in North America. For example, if you look at this slide, we have about 120 million tons of biomass produced annually in Canada, including forest, agriculture, municipal solid waste. And it's very good to see that about 85% of Canada's pellet production, equivalent to 1.3 million tons, is exported every year. And this biomass energy usage leads to CO2 recycling process, as you see here. It could be biopellet or biofuel, but nonetheless, that if we use biomass for energy production and usage, there is a kind of more or less CO2 neutral process. And when you're looking at the usage of biomass, we are looking at mostly the residue that are not for food, for example. So the biomass sources that we are looking at is agricultural and crop residue. That's what the main focus of this research. But nonetheless, we have sewage residue, municipal solid waste, animal residue, industrial residue, forest crop and residue. So the usage of this material is very useful because they are renewable, they are clean, and they have very low emissions, and they are more or less carbon neutral. And most importantly, this is more or less uniformly distributed around the planet, unlike the fossil fuel. So this slide shows the renewable energy and biofuel generation in the world and by region. So you can see the one in the left that we have a lot of hydropower, wind, and also the one in the yellow deals with the biomass. And the one in the right, you see the biofuel production by region. North America, South America, and Europe, they are quite advanced, especially for last 15 years or so on the bioenergy production. And if you look at this this particular slide, it says the global ranking and export of biofuel pellet in 2017. So you can see the Canada is, though it's a small country, we are able to produce about 12% of the world biopellet and generate about $400 million per year. And among these different provinces, British Columbia is the leader, followed by Quebec, followed by New Brunswick, Alberta, Nova Scotia, and Ontario. So we can see that a lot of these biofuel pellets, as you see in the right side, are exported to various countries. So this slide shows the trend of pellet export. So in Canada and the US, and over last 7-8 years, you can see the export has almost tripled in US and almost doubled in Canada. So in this project, our focus has been to use the agricultural residue for biopellet production, and these are oat hull, barley straw, canola hull, canola meal, and also mustard straw. So the strategy of this research has been twofold. One is to take these biomass precursors, the canola hull, oat hull, canola meal, barley straw, and mustard meal, and then use them through or process them through a hydrothermal and torrefaction pretreatment process, and then co-pelletize with and without original precursor, and also the torrefy the post-treatment material, and then get to the useful product from this material, such as syngas through gasification technology. So now let me tell you a little bit about this hydrothermal treatment, and also the other treatments that we have processed this biomass through. So if you look at the slide or the graph in the right, it's a two-page or the phase diagram for water, for which basically pressure versus temperature. We find that after the critical point, which is about 22 megapascal and 374 degrees C, we get supercritical water. And when you treat the biomass through this process, we get methane-rich gas or hydrogen-rich gas, depending on what pressure, what temperature you're putting it through. And if you look at the bottom here, which looks at the hydrothermal carbonization, that's where we generate a lot of biomass with a large amount of carbon, and that translates to the one in the left, the hydrothermal pretreatment, where the temperature varies from about 100 to about 300 degrees Celsius to carbonize this material for pellet production. And if you look at this slide, we see the effects of temperature on torrefaction of lignocellulosic biomass. We have lignin and hemicellulose, cellulose, which are the main components of biomass, and they go through different degradation processes as we increase the temperature from 200 to 300 degrees Celsius during the torrefaction process. And when we look at the biochar production before we pelletize it, and then the nature of this product depends on the nature of the precursor, and also the hydrothermal condition and torrefaction condition, including the temperature range, including the heating pattern, and also the way we treat them in the reactor. So if you look at the torrefaction technology, as you see here, the temperature varies from 200 to 300 degrees C, and the time is 10 to 60 minutes, up to about 1 hour with inert gas. And so if you look at the original biomass that I showed before a few slides, they have high moisture, they have low calorific value, they are hygroscopic, poor grindability, high volatile content, high volume, low bulk density, non-uniform properties. And as soon as you put through a torrefaction process, then this process not only gives the condensable liquid and non-condensable gases, but it also gives the high quality torrefied biomass, which have these properties: low moisture, high calorific value, hydrophobic, better grindability, low volatile content, less volume, high bulk density, more uniform properties, unlike the original biomass. And once you torrefy this biomass, you can see that it has many applications. You can do the pyrolysis, combustion, and you can apply for metallurgical application as well. You can gasify, you can co-process. There are a lot of things that can be done with the torrefied biomass. And what are the factors affecting the quality of biomass? The properties of high quality pellet include the dry, hard, durable, high heating value, high mechanical strength, high hydrophobicity, and low ash content. And the quality of pellet depends on many things here: the particle size, the moisture content, initial moisture content of the biomass, the pre-treatment methods, operating conditions for pelletization, post-treatment, chemical composition of additives, chemical composition of feedstocks. And in this one, the progress that we have made, as I mentioned in the beginning, we have completed the milestone 1, which deals with the production of torrefied biomass and hydrochar from agricultural residue. And we also have completed production of fuel pellet from treated precursor. And currently, we are working on the gasification process for fuel grade syngas production from the biomass pellet. So the technical accomplishments in this work are the production of pre-treatment precursor, co-pelletization of hydrochar with canola meal, co-pelletization of torrefied biomass with a mustard meal. So I'll just show you some results very briefly. Please don't get bogged down with the numbers, but I'll just highlight that when you look at the making the pellets through hydrochar through the different processes, we look at the elemental analysis and proximate analysis, and also calculate the higher heating value. So you can see that for the oat hull, the barley hull, and canola hull, the higher heating value is about 17 to 18 megajoules per kg, and they have roughly 2.5 to 9% moisture, and ash content 4 to 7%, and a lot of volatile matters. You can see about 85%, 60 to 85% of volatile matters. And about the canola meal, it has a little bit more calorific value, about 15% more, 20.4 megajoules per kg. And they also have, you can see the moisture about 8%, and volatile matter is a bit less here, about 72%. And let me go through how do we produce this hydrochar through a high pressure, high temperature power reactor. So what we do is we subject the biomass through temperature range 210 to 270 degrees C, and you can see we put a little bit of pressure, which is generated through naturally by heating the temperature due to the water present in the biomass and or the added water in there, and then the reaction time is roughly 90 minutes. And once you produce this torrefied biomass, um, or the torrefaction of the biomass that we conduct in a benchtop microwave hot oven reactor, as you see here, and the power range is given, and the nitrogen we do it in inert atmosphere, and the reaction time is 20 minutes. So we're producing torrefied biomass as well as the hydrochar through this carbonization process. And once we do the torrefaction through the micro oven, you can see that that we have ballistra, oat hull, and canola meal, and we subject the temperature these to three different temperature: 220, 260, 300 degrees C for 30 minutes and 60 minutes, and you can see how physically they look, and they gradually produce char, and which has a more carbon content or less volatiles, less moisture, etc. And again, these are a lot of numbers, but all I want to tell you is that for the oat hull and ballistra and canola hull, so you can see when you subject that to about 300 degrees C through torrefaction process for about 60 minutes, we increase the higher heating value from 17 to 20, roughly 23 or 25 megajoules per kg. So that is one conclusion from this. And also the energy density, which is the density of energy for the product over the energy density of the feedstock, it has gone down, gone up about 37% and 42% in some cases. So you can see that energy content density is also increased after this torrefaction process. And also the mass yield and energy yield is also varied when you subject this material through torrefaction process, and we find that the mass yield, which is basically the final weight over initial weight, and here is the energy yield, which is the final weight of the biomass times final higher heating value over the initial weight of biomass times initial heating value. So they are kind of different as you subject that from 220 to 300 degrees Celsius. So in some cases, you can see the energy yield about 92%. And when you subject to very high temperature, both the mass yield and energy yield goes down. And again, this is a very clouded slide, but all I want to say here, just please look at this first one in the left, where we can see that when you subject that to the biomass to higher temperature, for example, room temperature to say 300 degrees C, then we have the removal of water and small volatile molecules, and that is also the hemicellulose, cellulose, and lignin are impacted gradually. And this one, again, is very, very crowded, but all I want to say that once you torify this biomass, it becomes hygroscopic, phobic, and the moisture uptake is reduced to some extent. So just wanted to conclude this part of the presentation. We find that the torrefaction increased the higher heating value of oat hull by 37, 42, and 32% respectively, and significantly reduce the moisture uptake rate and make the material hydrophobic. And the TGA analysis showed that the torrefaction process makes this material thermally stable, and of course, again, stated that becomes hydrophobic. So then we take this torrefied biomass and we wanted to densify with, again, these are the precursors, canola hull, canola meal, oat hull, and here is the bench scale extruder that we used with the biomass to water content varied from 1.75 to 2.5. And also we used the canola meal as a additive 50 by 50 on the weight basis. And so we mix them in this with these parameters, and then subject to a bench scale extruder to produce the pallet. And here is the material, the hydrochar, and also the hydrochar, and also the one mixed with the canola meal 50-50, and here is the biomass to water ratio, and here is the relaxed density, which is the density that is measured after 2 weeks. So what happens is when we make the pallet, the density is a bit higher, and after 2 weeks, it expands to some extent. We found that this density is much more valuable or appropriate than the density if you measure just after you palletize. And again, if you look at the different precursors, hydrochar to canola meal ratio, and the relaxed density mechanical durability, we measured all that, and we can see that in some cases it's very, very durable, and it's basically durable, and the property is way better. And this one shows that the optimization of biomass to water ratio, and we find that with the canola hull and with this water ratio of 2.5, we find that the breaking force, which is the force that is applied to break the pallet, and here is the impact resistance, and here is the high rating value. You can see that this is really good material. And also we look at the co-pelletization of torrefied biomass with the mustard mill. Again, this is a new material we wanted to test, and we find that the high rating value is good. The moisture uptake is low to some extent after we made the pallet, and then the relaxed density is also very good, and the density you can see it's pretty good as well. So what is the relevance of this work for industrial applications? We find that in 2019 the total production of canola, barley, oat were 19.5, 10.4, and 4.3 million tons respectively in Canada, and 10.9, 4.4, 2.2 million tons in Saskatchewan. So it's about half of Canada's production in all cases. And the amount of canola hull collected is about 10% of the product. So you can see a lot of this material are generated in Saskatchewan, and then the oat contents again about 20 to 30% oat hull. So the idea is to use all this material to produce high quality pellet. And the relevance to Canadian scenario is the Canada's per capita greenhouse gas emission is about 20 tons of CO2 equivalent, which is one of the top emitters in the world. And co-firing of fuel pellet with coal is a promising method to drastically decrease the greenhouse gas emission from coal-fired power plants. And these pellets can also be used for export to Asia and Europe to produce revenue from agricultural residues. And there are many critical success of this project to improve the pellet property. Use of pretreatment instead of additive decreases the final cost of produced fuel pellet, and low price fuel pellet would be a strong candidate to replace cheap coal in the fuel market. And these fuel pellets produced using thermochemical treatment will be a coal-like material which can be easily co-fired with coal in power plants to reduce environmental impact of this industrial process. And production of high quality fuel pellet from low value agricultural residue with a strong market for their export to other countries is attractive and beneficial to farmers and the country. And also there are technical challenges. One is the looking at the mechanical strength, moisture resistance, higher heating value of the pellets. These are very, very important to decrease the biomass fuel pellet production cost, optimization of the process condition of treatment process, and appropriate design and scale up of this process as required, and use of agricultural residue for production of biomass fuel pellet provides a new source of income to farmers. Export of this product to other provinces and country again is very attractive. And this is kind of the flow diagram for fuel pellet production. You can see we have the collection of the raw material and chopping, etc., hammering through a hammer mill, and then the microwave system for torrefaction. And here is the torrefied biomass, and then you grind them. And here is the mixing of the biomass with the additive, and here is the pelletization system, and then the pellet characterization to meet the standard, and then used for gasification. And that's part of our project, but they can also be co-fired with the coal for producing power in the coal-fired power plants as well, even for home heating for that matter. And so the future work is looking at the optimization of biomass pellet gasification process for fuel grade syngas production. And we have also projects on the conversion of syngas to transportation fuel or the jet fuel. So that basically goes very well with the other projects. And we also want to work on the scale up and piloting of the new pelletization gasification process with the WED funding. We have a process to get a palletizer from Sweden, and that's in the that should be arriving fairly soon, so that we can look at pilot or the scaling up with our recipe to produce large amount of pallets. So then we want to work on the life cycle and techno-economic analysis of biomass pretreatment, pellet production, and gasification process. So what is the take-home message? So we want to use the pre-treatment, which not only can produce high-quality fuel pellet, but also makes their final price more competitive compared to that for cheap coal. And the technical accomplishments include the treated precursor were produced, co-pelletized of treated precursor with canola meal was successful. Relevance, these fuel pellets when used as a carbon neutral fuel can effectively decrease the emission of greenhouse gas from power plants and also bring revenue to farmers and also bring revenue for the country as well. So these are the some of the equipment that we have in the lab. The one in the red, you can see that we use for this project. So we have large amount of equipment infrastructure, and here is the second slide. So you can see that we have all this in the lab, and just wanted to bring that to your attention. And that also helps to do some collaborative research. Because of COVID-19, we're not able to collaborate effectively with our partners, in the sense the academic partners in UBC and other places. So as soon as things become normal, we want to take that to the next step. And this is a very, very important slide. I wanted to acknowledge the funding from the Government of Canada under the Canadian Agricultural Partnership, BiofuelNet Canada, Saskatchewan Ministry of Agriculture, ANSHIRC, Canada Researcher Program, Western Economic Diversification, which allocated $1.3 million to have new infrastructure related to this and other projects. Canadian Light Source for helping us to characterize the material more at the fundamental level, Saskatchewan Structural Sciences Center, Saskatchewan Research Council, SaskCanada, and most importantly, our industrial partners, BiofuelNet Corporation and Hey Holding, and also Provita Nutrition Limited. And this is the research group. Most of the work was conducted by Tumpa. She's here. And also we have some students already graduated, and Sima is here. So she also did some hydrothermal work. And many people, Jude here, who is involved in the gasification. So we have a lot of people contributed to this project. And with that, again, thank you for your attention. And I hope it was useful to you. And we can certainly talk about, discuss on this. We have some time. Thank you so much. And thank you again for your attention.
Okay, thank you very much, Jay, for a very informative presentation. And it seems that you have a big research group, right? So lots of people are working with you on these projects. Great. So we already have a couple of questions here, Jay. The first question is that what is the yield of the process? How much material did you lose during the process?
Actually, we have done the mass balance for most of the experiments. So when you do the torrefaction or hydrothermal process, so our main product would be the moisture release, volatility release, and all that. So we want to increase the carbon content of the material. So the yield is a bit lower because of those reasons. I think if you don't mind, I'll show you that mass yield slide, and that gives the direct indication of what was the yield of this material. So you can see this one, the mass yield is through the thermal torrefaction process. You can see it varies from 44 to 42 to 68%. So this is what we have here.
Okay.
Yeah.
Thank you. And a follow-up question: did you use any binder to achieve such a high durability?
That's a really, really good question. I think we did a lot of work on the binders in the previous project, BiofuelNet project, and here what we try to do is stay away from binder, because binder costs money, and we wanted to just take the torrefied material and then use the canola meal or the mustard meal to put them together to create the biopellet. And in these cases, we have not used the binder what I presented today.
Okay, so just a quick question, Ajay. You mentioned canola meal. Is that the same canola meal that already has an established market, or this is part of the base in the canola oilseed crushing process?
Actually, it's a good question. The canola meal that we get in when we cross the canola, we get a canola meal which has about a lot of protein, and they are used for animal feed. But I think in the province we have a surplus quantity of canola meal, So what we try to do is remove part of the oil from the or the protein from the canola meal through solvent extraction process, reduce that to some extent, and then use that for fuel pellet production. The canola meal has a really good market, but because of the surplus quantity of canola meal, we are trying to use part of that for fuel pellet production.
Okay, great. So another question about the ash content, Ajay. The ash content of the torrefied material is much higher than the raw material. The European Union quality standard for fuel pellets requires ash content of less than 1%. How do you plan to attain lower ash content?
That's a really good question. We know that the ash consists of inorganic materials and alkaline materials, all that. And when we torrefy, this ash really does not go away. It stays within the material. And that's why in this slide, you see that ash content increased drastically. For example, from the original value of 3.8 goes to 9.2 and all that. It has to go through maybe I have to go and look for a proper method, but we have to find ways to reduce the ash content of this. But if you are going to use this mammoth for cogeneration using with the coal, for example, the ash content would not matter. And if used for home heating, maybe ash content doesn't matter. But in some cases, I think the ash content should be much lower. And if the ash content is lower, the energy value is also going to go up. So for certain application, we can don't have to do anything for the ash, depending on the application. But in some cases, you are right. We have to look at reducing the ash content. But I really don't have an answer. How do we go to less than 1% from the original 3.8% in the product? And because these are agricultural residue, they would have more ash in comparison to the forest residue that is generated or that is used to produce fuel pellet in Canada and for export purposes. But when you use this agricultural residue, we are bound to have more ash, and we have to find other applications that can tolerate this high ash content.
Okay, thanks. Next question is about the tar. How about the tar production and pollution in the process?
That's a really good question. When you look at the torrefaction in microwave, and we do that up to torrefaction from 100 to 300 degrees C, we don't see really any tar production. And that carbon or the tar, we need a little bit higher temperature to produce. And the whole idea here is to look at degrading or removing moisture volatiles to some extent, and also reacting some of the cellulose, hemicellulose, or lignin to just mild treatment. And we basically not producing tar through this process. But if you go to higher temperature, for example, through gasification, and then you produce tar. And in the hydrothermal process, when we have autogenic pressure and temperature, we don't produce tar there as well. And whatever we produce partly stays with the liquid, and we are more focused on the solid product. So it has not been an issue with us so far.
Okay, thanks. So next question is about the barriers to commercialize the torrefaction. What barriers has to be overcome to make torrefaction a commercial success?
Can you please repeat that question?
What barriers have to be overcome to make torrefaction a commercial success?
Again, that's a really good question. I think when we do the techno-economic analysis, we have to look at what are the real barriers, and what is the logistic. I think you specialize in the value chain and also the collection and distribution, etc. So we have to see which part of the process consumes lot more money, and how that can be tackled. So we have not really gone that far, but all we had focus now is to look at the potential biomass for biopellet production, and will this be commercially viable? We do not know, and which part is the bottleneck? We do not know that yet. So that will be the next part, and that study will be based on whatever we have found so far.
Okay, thank you. Next question is, wheat is largely planted in Canada, especially in Western Canada. I wonder why wheat residue is not considered in this research.
Well, that's really, again, a good point. We basically focused on this based on the industrial interest we had, what our partners wanted, and they're also putting part of the funding on the table. I think that's really good one to look at using for this project, for the biopellet project. I completely agree with that.
Okay. Ajay, the next question is a very high level question. So if you don't have the answer, I can actually jump and answer this question. Could you please let us know how much of the electricity energy in Canada comes from biomass?
It's almost zero, I think. You mean the agricultural biomass?
No, I guess it's this person is asking like general in Canada, like any type of biomass. I'm assuming woody biomass, agricultural biomass.
Yeah.
Yeah, for bioenergy. Yeah, for electricity generation.
Yeah, I think when you're looking at that 13% of energy coming from the biomass, from the renewable sources, I think we have a lot of hydro. There's some nuclear. From biomass to energy, that data I don't think I have right now, but that's a good one. Thank you.
Yeah, Ajay, I can actually address that question. So 1.7% of the electricity in Canada come from biomass. Okay. And most of that biomass is actually coming from woody biomass in pulp and paper industry. Like we are not using any of agriculture biomass at the moment for bioenergy production. So it's mainly woody biomass is actually contributing to the production of electricity in Canada. So a couple of more questions are coming. I guess we have still time to address the question. Yeah, again, I just want to clarify that. So 5% of biomass in Canada is that's a contribution of biomass in total energy production, but for electricity it's less than 2%. So I just want to make sure that this is for electricity generation. So next question, it's about, so the carbon monoxide gasification biochar and biomass increase ratio. This is a question, yeah. The gasification biochar and biomass increase ratio hydrogen to carbon. I'm not sure what exactly is the question. Can you see the question, AJ?
I have to go back. But what I understand, you can maybe ask the person to ask the question.
I think he's asking about, can we use green hydrogen in the process for the biochar and the production?
Absolutely. I think I got the question. The question is, can you produce high quality hydrogen through gasification of biomass? So when we gasify the biomass, depending on the temperature, depending on the steam to biomass ratio, depending on the residence time, we can vary or we can manipulate the composition of the final product. So the hydrogen and to CO can vary a lot. And when you look at the coal gasification, for example, in South Africa, for the production of syngas and a conversion of syngas to transportation fuel, the the carbon does not, the coal does not have a lot of hydrogen, it has a lot of carbon. So I think most of the hydrogen comes from the steam in that case. And for the transportation or for the gas to liquid technology, hydrogen to CO ratio requirement is 2. And for the ethanol production, it is 1.25. And so how this hydrogen to CO is manipulated through water gas heat reaction. So we take hydrogen, this hydrogen or the syngas, and subject it to water gas heat reaction to increase the hydrogen content in the final product. So a lot of this CO can be completely consumed to produce hydrogen, high quality hydrogen through this water gas heat reaction process. So the answer is yes, it's possible. And of course, you need that second step to convert the carbon monoxide to additional hydrogen through water gas heat reaction.
Mhm. Okay, thank you. And another question is that I would like to know if the content level of chlorine was measured to know if it's too much, is too high, and would lead to problems like formation of hydrochloric acid, corrosion, etc.
Mm. When you look at Mahmoud, about torrefaction process, we are basically doing it up to 300 degrees C in presence of inert gas, which is nitrogen. So that does not allow us to produce any acid in the system, and because of the we are not producing any liquid as well. So as soon as we produce the moisture and volatiles, they leave the system. So the system is more or less intact, and basically the preventing from corrosion in this system. Um, but and also we have basically in the microwave we use a boat that contains this biomass, so that it's a kind of nitrogen going in and out through the system at certain power for microwave one. And we have not seen really much corrosion in this unless you go to very high temperature for this material.
Okay. Thank you very much, Jay. I don't see any more questions are coming in, and we still have a couple of minutes left. But if there is no more question, Jay, I want to really thank you for both presentation, one you had in December and the presentation you had today. And we see that there is definitely a great opportunity to use agriculture biomass, but we know that we have to improve the quality of agriculture biomass, especially by removing the mineral content. So this type of research is very critical for producing a feedstock for bioenergy, biofuel, and other bio-based product applications. So Ajay, do you have any final comments before we wrap up the webinar?
Well, I just wanted to thank you for coordinating this talk, and also thank our colleague Ian Don Smith and McGill for taking the leadership in this project, and all my collaborators, and also all my academic colleagues who have been working in these areas. I think it's very, very important for Canada to look at or contributing to reduce the greenhouse gas emission. And all this discussion we had today, we'll certainly keep that in mind, and hopefully that will increase the quality of our work. And we are always open to collaborative research, like many of my colleagues in Canada. And it'll be an honor to work with some more people. As I showed that we have a lot of equipment in the lab, and those who are interested to use some of these are most welcome to make use of these for their own research, for their own academic advancement. We'll be happy to receive any comments or email, and open for collaboration. And also we're looking at more industrial opportunities as well to contribute to Canada's effort to reduce the greenhouse gas emission. And because of the COVID-19, we went a bit slow. We're a bit slow. Hopefully, to hope to ramp up our work. And a lot of people are graduating in the meantime, so always looking for high quality people to recruit for our research, and also look forward to collaborating with some academics as well. And again, as I mentioned during my talk, wanted to have a separate conversation with our colleagues in UBC and see what we can do together, especially in this project and similar projects. Thank you.
Okay, thank you very much, Ajay. But before let you go, there is only a very quick question that we just got. The answer is very quick. So what supplier did you get the pellet mill from Sweden?
I'm sorry?
What supplier did you get the pellet machine? You mentioned you got a new pellet machine. What's
Yeah,
the name of
I think Mahmoud, we talked about it. You and I, the same one that you have for UBC. I have to check the name of the supplier.
Yeah, I forgot it. I guess it was the SPC unit, right?
Yeah, SPC. Yeah,
Yeah,
SPC. It's called SPC Pallet Mill, I think.
Yeah. Exactly.
SPC Pallet Mill. I think that is the name of the company, or yeah.
Okay, thank you very much, Ajay. Thanks also, thank you all the attendee. They participated in this webinar. Again, the great discussion and very good question. And hopefully we see you in next week at the same time for the next webinar, which is actually about the production of sorghum on marginal land. So the focus is going to be the production of biomass on marginal land in Canada. Thank you very much and have a good day.
Thank you, you too. Bye. Bye. Thank you. Thank you, everybody. Bye.